Okay, hey folks, welcome. I am Bethany Ellman, Professor of Planetary Science and Director of the Keck Institute for Space Studies, and I want to welcome you to our lecture series. Many of you are long friends of the Keck Institute for Space Studies, or KISS, but for those who are not, KISS is Caltech's Think Do Institute, whose goal is to revolutionize space exploration. That is, how we make measurements, how we explore, what technologies are used, what questions can be asked and answered by technologies, not those that are available today, but those that need a decade of development. So we seed early stage ideas and developments across all areas of the space endeavor at Caltech, whether it's in geological and planetary sciences, engineering and applied sciences, physics, math and astronomy, or the chemistry and biology of what's going on, really all aspects. So today, I am delighted to introduce one of our KISS affiliates. In addition to our study programs and our lectures, KISS has a cohort of grad students and postdocs. And so Zach Chase is a PhD student in materials sciences here, working with Professor Kathy Faber. His expertise is on ceramics and high temperature ceramics like you would use in a spacecraft re-entering the atmosphere. So pretty cool stuff. We're delighted to have him as an affiliate, and he is the master of ceremonies today. So without further ado, Zach.
Thank you, Bethany. It's my pleasure to introduce today's speaker, Dr. Christian Frankenberg, the Chanley Family Professor of Environmental Science and Engineering at Caltech and the principal investigator of the Carbon Eye mission. Dr. Frankenberg has over 20 years of experience in remote sensing of atmospheric trace gases with a focus on methane, carbon monoxide, and carbon dioxide. His work has spanned algorithm development, spectroscopy, and mission design, contributing to advances such as the proxy method for methane retrievals, improvements in spectroscopic accuracy, say that 5 times fast, and the development of solar-induced chlorophyll fluorescence retrievals from space. He's led both targeted and wide-area airborne campaigns for methane point source observations, including the first controlled release methane experiments and surveys over the Four Corners regions. He also organized a global methane workshop at Caltech and is currently the principal investigator of this Carbon Eye experiment, currently in a NASA Mission Concept Phase A study with future down selection by the end of this year. Today, he'll be presenting Unseen But Measured, Carbon Eye's global mapping of trace gases, offering an inside look at the next generation mission to resolve carbon fluxes at sub-kilometer scales across the globe. Please join me in welcoming Dr. Christian Frankenberg.
Thank you so much, Zach. I hope you can hear me well in the back. Everything fine? So it's my pleasure today to talk about the carbon investigation, a brief carbon eye. You might see that there's a little bit of a wink of an eye in there in the O as well. You can kind of interpret this as you wish. One advantage of running a big mission is that you have access to good graphics designers. So this is kind of our title page logo of the investigation. But before I move on, I will just give you a brief overview of what I'm going to talk about. First, I should explain a little bit what this Earth System Explorer call is, which is actually demanded by the National Academy of Sciences through the Decadal Survey. So I'll give a brief overview of this. Before jumping into a brief overview of Earth's carbon cycle, because that's in our name, so that's mostly what we are attempting to study. And then I will move on to big picture questions on atmospheric CO2 and methane. Methane is a little bit more our focus area. I will spend somewhat more time than usually today on the CO2 part. Then we have to argue, why do we need another space-based mission? First, we have to identify, of course, what are the big gaps in the current space-based observational system? Why don't we answer the questions already that we want to answer and that are asked in the Decadal Survey? And how can we fill these observational gaps with a new mission, such as Carbon Eye? But we can do much more. Often they use imaging spectroscopy. They call it kind of the Swiss Army knife of instruments. So you can not just do atmospheric science, but you can also do surface science, plastics, vegetation, and all kinds of other things that we will be exploring with that instrument. And last but not least, I will give you a little bit of a glimpse in the hardware, because we have built a demonstration unit at JPL, which is pretty exciting. So I'll show like a time-lapse movie of that development at JPL. But to jump into the Earth System Explorer call, this is taken straight from their website, which is here, which is the call for proposals, basically. And it's basically an Earth System Explorer call that was recommended by the National Academy of Sciences through the Decadal Survey. So the Decadal Survey, which is kind of many scientists contributing to that document, they tell NASA what to do, so to say, from a science perspective. And they say that they have addressable target observables that they call TO in the Decadal Survey. They want to be specifically targeted by these kind of Earth System Explorer missions, which are not Battleship Galactica missions. They are more focused and targeted missions that basically tackle specific science questions. You might think about the Decadal Survey whatever you wish. There's some things I like about it, some things I really don't like about it. They have a list of different questions. They sort them how important they are. The problem is sometimes that these things take decades to actually be implemented, and sometimes these questions are not really the best questions anymore. They don't age well, so to say. But overall, their overall scope is usually pretty good, and one target observable is greenhouse gases. This is where we fall under. We also have different topics that we cover. Where I fully agree with are some statements in the summary of the Decadal Survey here. One is a central question for CO2 is the role of the terrestrial biosphere as a sink to moderate the rise in atmospheric concentrations. This terrestrial sink is poorly quantified. So this is a fundamental science question, has nothing to do with quantifying anthropogenic CO2 emissions. It's more about how the natural carbon cycle reacts to perturbations in the system. The second one has to do with methane. For methane, there are very large uncertainties in the factors controlling wetland emissions and the magnitudes of different anthropogenic source sectors and regions. And I'll go into that a little bit later as well, why the uncertainties in anthropogenic methane emissions are so much higher by kind of 2 orders of magnitude compared to CO2 emissions. To do that, I have to give you a little bit of an overview into the big picture question, which is moving into the Earth's carbon cycle, which basically modulates the response to these perturbations in CO2 and methane. And however, it's much, much bigger than that, because in principle, we have the Earth's carbon cycle. This is the typical image from the IPCC here, where we have photosynthesis actually generating the biggest fluxes on Earth in terms of moving carbon around, of around 120 petagrams of carbon being taken out of the atmosphere every year through photosynthesis. And photosynthesis basically drives most of the biogeochemical cycles on Earth because it uses sunlight to convert it into chemical energy and releases O2 in the meantime. This actually triggered the Great Oxidation Event roughly 2 billion years ago. Without photosynthesis, we would be living in an anoxic world, and the world was anoxic before photosynthesis was invented. On top of it, it converts sunlight to organic carbon that basically feeds life and after burial powers the industrial age, which is basically the reason why we had the Industrial Revolution. It was due to the effects of photosynthesis and buried carbon deep underground that basically enabled us to use it as fuel. Respiration basically closes most of that loop. So most of this per year is basically respired back into the atmosphere through aerobic decomposition, which is basically turning organic carbon back into CO2. Usually, like in our body right now, it's enzymatically controlled combustion. A human has about 100 watts of power, so we have to maintain that. And this is mostly done by food. This is not a low energy. We are not a low energy organism, so we need oxygen and organic carbon to basically power us with 100 watts. But there are lower energetic mechanisms as well, specifically when once oxygen is lacking, and when it's lacking, you can turn organic carbon into methane, which is basically giving you a much more potent greenhouse gas in that effect that also relates to CO2, to the carbon emission. Fires basically close the rest, so part of this is kind of uncontrolled combustion, and that releases, of course, carbon in the form of CO2, methane, and CO, depending on the combustion process itself. Now, what we do want to see is how does this natural carbon cycle react to a perturbation to the system? And the biggest perturbation that we do right now, we emit a ton of CO2 into the atmosphere, and we want to see how the carbon cycle reacts to that. To do that, we first have to basically look at the anthropogenic emissions and the magnitudes thereof. This is simple upscaling estimates from IPCC guidelines that every country provides, but there's actually no cross-validation as to the methods that they use. And we see now that overall the total emissions, if you sum all the countries together, we have about 40 gigatons of CO2 per year as emissions. Just as a reference, what is a gigaton? It's the same as a petagram. And a gigaton is roughly the weight of a cubic kilometer of water. So it's quite a big big mass. What we see is that, oh, no, this is not what I wanted to do. What we see is that by now, in about the year 2000, China overtook the European Union in terms of CO2 emissions, and in 2005, it overtook the US. And now it's more than double the size of the US emissions in here. So most of the developed countries like the US and the European Union have actually declining CO2 emissions. You also see that you don't see election cycles in there, in these things. Usually they are run on very different timescales than what the administration can actually change. And you see that a lot of these emissions are co-varying between different countries, meaning that most of these variations from year to year have more to do with like global economic shocks to the system than actually what policies are being implemented in different countries. And if you count China per person, it's still far below what the US is doing. So this is just, there's a lot of people living there and they slowly ramp up their per person CO2 demand. The question now though is, using this one, we could expect or calculate how much we expect to see in the atmosphere. How do we do that? We have these emissions in here. We have about 1.8 times 10 to the 20 moles of dry air in the atmosphere. You can trust me on that. This is a rough ballpark number. So this is basically the mass of the atmosphere in terms of how many molecules do we have in the atmosphere. This is a number I think that even like skeptics could agree on, that there's a certain amount of molecules in the atmosphere. And 40 gigatons of CO2, I hate these units. I wish we would move everything to moles. Would make our life a lot easier because it's so easy to make errors there. 40 gigatons of CO2 is about 9 times 10 to the 14 moles per year of emissions. If we have that, we just have 9 times 10 to the 14 divided by moles per year divided by 1.8 times 10 to the 20 background. This gives us an increase that should be around 5 ppm of CO2 increase per year. Just by doing a bookkeeping exercise that everyone could do on an Excel sheet. And this is usually the most convincing argument that you can give to people that, yes, we are causing an increase, because we can compute what should happen if we emit that many CO2 molecules. Do we see 5 ppm increase in the atmosphere? If we would see 20, then I would be a skeptic and say this can't be us. What we see is, though, only 2.5 ppm per year. So we see about 50% lower increase of CO2 in the atmosphere than we expect. What we would expect from a bookkeeping exercise like this is a straight line like this that would have a slope that would be twice as high as what we observe. This is kind of what we call the airborne fraction. This is the number of the fractional contribution of what is actually staying in the atmosphere. So it's usually around 50%. So the increase is only 50% as strong as we think it should be given our emissions. So where does the rest go? It's mostly going into different parts that we often only compute through residuals. So if we have the total amount of fossil fuel emissions that we think we know roughly well, because you basically just count how much gas and coal and whatnot you emit and burn, plus some somewhat more uncertain land use change estimate, we can then divvy it up into the different sinks where it goes. So we've seen only roughly 50% goes into the atmosphere. And the current state of knowledge is that the remaining 50% is kind of almost evenly split between an ocean sink and a land sink. The ocean sink is thought to be better known because it's a more physical process of CO2 just diffusing into the ocean because we have a stronger CO2 gradient building up in time. The land sink is a little bit more iffy because it's biology driven. It's really photosynthesis and the biosphere that basically reacts, and that is way harder to predict than a physical system like the ocean. If we dig into the land sink, we could compute, we could basically integrate the accumulation over land and assume where does all the carbon sit? Can someone go and see where the carbon molecules on land? It must be in plans somewhere. So can we observe this? And Dinon Baron, who was kind of a Schmidt postdoc here at Caltech with us for quite some time and is now back at the Weizmann Institute and has a great position there, he basically wrote a paper published this year in Science on recent gains in global terrestrial carbon stocks. What we think should be happening in the land carbon sink using this calculation here is a graph like this, where we accumulate almost 35 gigatons of carbon over that time period. What we observe from satellite measurements, though, are different diversity of satellite measurements over time that are used to estimate above ground carbon stock, is an increase that, if we start from here, is only a fraction of what we assume is happening or should be happening and be observable from space. That basically has a conclusion that it's probably not in the above ground living biomass, the enhancement in the lancing, but it could be in dead pools like the soil or reservoirs or other reservoirs where it could be stored. But it has a tricky implication. The most important one, and this is kind of rattling the cage of the lancing question and basically rephrases it of what would be the best observations to constrain it. What Inon was doing, it reports that the lancing is reflected in non-living biomass, not above ground biomass. That means that we can measure above ground biomass and their changes, but it's not that meaningful to get a better understanding for the lancing if this is not the main part of the lancing. So it's much harder to measure anything that's below ground from space, especially carbon. There's no real technique to do this properly. There's another paper that should come out this year sometime in the last review process from Jim Randerson, who was also professor here at Caltech before and is at UC Irvine. He actually hypothesizes that there are countries that over-report CO2 emissions and that the true CO2 emissions might be lower than we think. Even though naively speaking, I was always of the impression we need to nail the CO2 emissions to the dot because we know how much gas we fill up into our tank and eventually all of this will end up as CO2. That should be easy. But he's saying that there is easily 7 to 10% of a bias in there. And there are reasons for some countries, especially authoritarian ones, to over-report emissions. There's some weird incentive structure. You don't want to look economically weak because GDP of a country is often directly related to the power production of a country. So if you don't want other people to see that your power goes down and you might be in trouble, you don't really report this. And there are other incentives that might go in there. But if the CO2 emissions are really not as high as we think it is, it has actually a dramatic kind of conclusion on the land sink that would be getting much weaker than it is. And the ocean sink estimate would actually go up in the absolute magnitude. It's a little tricky to explain, so I'll just stick to that part. But the consequence of this one is, ironically, to constrain anthropogenic CO2 emissions would help the most to resolve this major puzzle. And to do this, and this is one part that Carbon I will also tackle, we can tackle the most uncertain CO2 emissions from power production. And this is often related to coal mines, and most of them are located in China right now. So constraining these emissions will actually help us greatly to understand the land sink, even though it doesn't measure the land sink directly. If you think that was bad, let's move on to methane because everything is even worse there. So we roughly know what the CO2 curve in the atmosphere is and where it's caused. And what causes it, this is the methane curve in here. This is at the South Pole. Most of the interannual variations here are due to changes in the destruction rate of methane, not in emissions here. But we had this increase in the 90s, and then suddenly in the year 2000 it leveled off. So we were kind of in steady state. That's when I did my PhD. And everyone thought like, okay, methane problem is solved. It's not increasing anymore. We can go home. We don't need to tackle it anymore. And it stayed stable almost perfectly for like 8 years. And then it started rising again. Then everyone put out a different paper. Oh, this is the tropics. Oh, this is this country, the stuff. There were like 5 or 10 different hypotheses for the first 2 years or so what caused the rise. All of them had to do with like strong interannual variations in some systems, but this just went up, going up and up and up. Usually if there's just one simple shock to the system, you would expect it to level off to a new steady state and then remain there. But it did the opposite. It actually started rising steeper in time, with the steepest rises kind of in 2021 and 2022. So what is causing this? Usually we all go like, oh, oil and gas, we see this fracking going on and whatnot. This must be it. There's one evidence in the isotopic ratio of 13C in methane in the systems that NOAA also measured, and it gets isotopically lighter in time. So this kink here, where methane started increasing, is kind of in line with the decrease in 13C isotopic composition. The problem is oil and gas related emissions are isotopically heavier, so they should actually cause like the opposite change in the isotopic end member. Microbially produced emissions of methane typically have a lighter isotopic composition, so this could give rise to like a decrease in the total isotopic composition here. So there's an indication that it's probably more related to microbial processes driving this. However, microbial doesn't mean it's not anthropogenic. So what happens in landfills or ruminants or rice paddies is microbial in nature, but it's anthropogenically generated. So they still classify as anthropogenic. But it could also be wetlands. Could be tropical wetlands that get warmer or systems that are in a feedback. To study this, we basically, these two key questions, carbon I is basically uniquely suited to do this. So what we want to have as science objectives, I will point through those later. We want to tackle things from the point source local scale. So these are things that we can now measure with instruments like emit and others, where we can basically see methane plumes at spatial resolutions that are much finer than 1 kilometer, what we typically have. And you can see basically the plumes directly. This is actually from a landfill in Iran. Naively speaking, before I thought of a landfill always like an area source, just seeps out a little bit of methane somewhere, but it acts as a point source in certain location, and this one here looks actually way worse than some oil and gas related emissions that we have observed. So we want to tackle point source scales. We want to tackle regional scales. This is the LA Basin. This is the CO2 simulation by Berkeley and the WRF-Chem simulation at 1 kilometer. But we also want to tackle regional and continental scale variations. This is the Amazon Basin, if you can detect the outlines of the continent here. And this is supposed to be happening in some areas where tropical wetlands are emitting methane. So our science objectives are basically to identify, characterize, and quantify hotspots of methane, CO2, and CO globally, quantify global monthly methane, CO2, and CO fluxes at the sub-100 kilometer scale. But most importantly, that's where the science is, really attribute and quantify the processes driving these natural and anthropogenic fluxes. Why do we need another mission to do that? There are some instruments up there in space, like OCO2, which is a NASA JPL instrument that tackles CO2 measurements. For all of these, we typically use absorption spectroscopy using the sun as a light source, and we measure reflected light, look at the spectroscopic fingerprints of all the gases, and thereby can deduce how much of this gas is in the column. GOSAT is a Japanese instrument, measures CO2 and methane. TROPOMI is a European instrument, measures methane globally almost at the daily scale. But we still haven't really solved these questions that I posed before. Why is that the case? So one tricky thing is that we are missing something literally and figuratively. This is an image of the Amazon. And if you go to images from GOES, which is a geostationary satellite, and look at the Amazon basin, it almost always looks like this. So you have these tiny little clouds in here. And if we zoom into this one and look at the footprint of OCO2, which is currently the finest spatial resolution dedicated greenhouse gas sensor that we have, it's the green one, and almost always you have some clouds in the field of view. So it's never a homogeneous scene. And for the retrievals and the accuracy that we require, we really need perfectly cloud-free observations. So there's hardly ever a cloud-free observation in here. You have to go to scales like the red dot, which is actually one of our global mode target, a global mode spatial resolution element. And if you see this little dot in the middle, this is what we want to target as a spatial resolution element for specific scenes. What is the consequence of this? When we did a study with OCO2 to actually see how many data points survive the filters fractionally, so you take like 100 measurements and how many survive the filter, the quality filter. In the tropics, you see this blue regime here. This is on a logarithmic scale. So in the tropics, you have data kind of yields that are less than 0.5%. In some areas, it's actually less than 0.1%. So there are some 100 by 100 kilometer areas in the Amazon where OCO2 had like 5 measurements over 8 years. That's how bad it is. And the same is true for TROPOMI and some of the other measurements. So the tropics are really, really very difficult to measure. That would not be a problem if they would not be interesting. However, the opposite is true. Where we hardly have any measurements, we have the highest uncertainty for methane fluxes. And we also have the highest abundances of above ground biomass. So we kind of almost have an inverse relationship of where we measure the worst. These are the most important regions on Earth. And without actually looking at the tropics, we can't really resolve these issues. So this is kind of the main motivation to go to fine spatial scales. So we really have to go much finer than we did before. Our basic approach is to use solar absorption spectroscopy, which enables, like the other missions, a high sensitivity towards the surface, but we focus on the 2 to 2.4 micron range, roughly. The advantage being that we can cover CO2 atmospheric lines, methane atmospheric lines, the cyan ones here, and the green CO2 CO lines. So we covered 3 different gases in one simple spectral range. This enables us to do point and area fluxes at the resolutions that we do have. And because we have multiple species as opposed to CO2, we can do chemical fingerprinting because the CO composition versus methane and CO2 is different for biomass burning versus kind of landfill methane emissions and other processes. I'll skip through this one here in the interest of time, just showing that we actually tested the retrieval algorithm with TCON data that were taken here in Pasadena in the Lynn Center, basically convolving the data to our resolution and still showing that it matches pretty well. The basic question, though, is how do we get to fine spatial resolution? Because fine spatial resolution is the only way to basically tackle the cloud problem. What we did in a study here that we called data drought in the humid tropics, how to overcome the cloud barrier in greenhouse gas remote sensing, we computed the difference between like a theoretical revisit time. This means how often is a satellite theoretically looking at a certain point in time. So if it's like one day, they should see the same location once a day. What we did, though, with the cloud filter is we computed, depending on the swath width and the spatial resolution of the element, what is the effective revisit time? That means what is the time in between two valid measurements that actually pass the cloud filter. And when we do this, we actually find a sweet spot in the 100 to 500 meter range of spatial resolution, because that is a range that's wide enough to give us a swath that can do a meaningfully high repeat time, but small enough to peek through the clouds. And this is basically the trade-off that we did to determine what kind of spatial resolution we need to do. And we gave ourselves a little bit of a thumbs up, even though we actually, this is another story. So what this means, if we zoom into a typical scene in the tropics, if you observe it at like 50 meter ground sampling distance, you see this sharp image where you basically can even resolve the cloud structure. So doing cloud filtering will be much easier because you kind of have a binary flag. There's a cloud, yes or no. There's almost nothing in between apart from the few edges. At 300 meter, which is our global mode kind of resolution, it looks a little bit fuzzier, but still kind of a binary cloud mask. This is tropomi at 7 kilometers. This is one of the key instruments that everyone is using. Here, in every one of these grid points, you have like a subpixel cloud. You can't really differentiate it. And then you basically have to throw away everything. You can't use anything. This reminds me, the problem that we now have, we have to read out incredibly fast. So we have to go to like 44 milliseconds exposure time to meet that spatial resolution. I took this screenshot from Stan Sanders. Many of you might know him. He was a great atmospheric chemist up at JPL. So he passed away recently in March this year. And there was a memorial here at Caltech for him. And Michio Okumura put up this slide, and it resonated immediately with me because I had to think about carbon-I trade-offs. And this is from Lord Porter, who got the Nobel Prize in 1967. This was more on chemical kinetics. So if you do atmospheric chemistry, it's very rapid kinetics, so you have to measure fast. And his statement was that the detection system was to consist of a rapid scanning spectrometer, and much time was wasted in the development of this before I realized that to demand high spectral resolution, time resolution, and sensitivity in a period of a few milliseconds was to disregard the principles of information theory. You can't have it all. So something's got to go to basically make it work. Or if you try to do everything perfectly, in the end, it will really not work out the way you expect it to work out. So what we did for this is actually finding the sweet spot in terms of spectral resolution, where our bandwidth is still wide enough that we get enough photon on a single detector pixel. Because to get enough photons on a single detector pixels within 44 milliseconds is a different beast than having a second or so for tropomi. And for that trade-off, we actually found that there's a sweet spot in between the 0.4 to 1 nanometer spectral sampling interval. And we had a design principle here of about 0.7 in terms of sampling that still gives us kind of a resolution function that is less than 2.5 nanometers or less than 2 nanometers as full width half max spectrally, which is the one that we need to actually differentiate different spectral absorption lines and not to confuse different gases from each other or surface features with the atmosphere. So this was this trade-off in here. But moving on to how this whole thing will then be implemented, what you see on the left is basically a typically sun-synchronous orbit, low Earth orbit, where individual lines are now represented by about 100 kilometer swath. Our swath width is actually a little bit wider than 100 kilometers. But we are tackling it as an imaging spectrometer. So we have about 3,000 cross-track spatial elements and about 500 spectral elements. In global mode, we bin about 10 of these cross-track spatial elements to have like a total of about 300 independent pieces of information in the cross-track domain. That gives us pixels that are roughly 300 meters wide, and we fly about 300 meters within our exposure time. So roughly speaking, the resolution element is 300 by 300 meters. That gives us a 100-kilometer swath. That gives us a revisit time that is better than monthly. So this is kind of the cadence that we wanted to have at least. With that resolution, you can't have daily observations globally. It's just impossible. You would need to fly multiple of those. In some areas, we might point to the glint spot as needed. We would do this only mostly at coastal areas where you might have methane seeps near the oceans. What is also very exciting, so the global mode is what runs most of the time. Every day we will do 3 different target observations in specific areas to improve our process-based understanding even more. And what we do for this, we do like a image motion compensation where we tilt the satellite while we fly over a target. This basically slows down the projection of the slit on the ground by about a factor 10. So we keep the same exposure time, but basically the slit projection on the ground doesn't move 300 meter, it moves only 30 meter. And if we then read out the entire detector, we get a resolution element that's about 35 times 30 meter at nadir, and we look straight down. This is kind of a resolution that is very unique for dedicated atmospheric remote sensing. And we can do this over an area that's of the size of the LA basin, about larger than 100 by 100 kilometers. Maybe I'm dating myself now a little bit. 100 by 100 kilometers when I did my PhD was a good resolution for atmospheric sounders. That was a single detector pixel. When I was at the end of my PhD, 60 by 40 kilometers was like, whoa, this is great. I think I could not have dreamed about like 30 meters resolution for atmospheric sensing. But I'm digressing now. To talk about what kind of observations we will take or what we expect to see in terms of gradients of methane and other trace gases, I just wanted to give you a few illustrations here. This is an example of tropical wetlands in the Amazon. So this is one of the most active regions in terms of global carbon cycling, where we don't really have a viewpoint. This could be a carbonized swath, and then we can see that within that here, we would have expected methane variations in the total column that are around 2.5%. That's about a change of 50 ppb. What we have as a guideline for our accuracy that we want to get with these kind of instruments, we want to be going down to 0.25%. And the precision numbers at the 12-kilometer scale, once we aggregate, will also be on that range. So we should have very high sensitivity to actually track these gradients in space and time over the Amazon, and thereby then figure out what is really emitting where and why in the Amazon basin, which is a very complex system. Most of this is most likely due to wetlands and fires. We can also look at the fingerprints of the different other trace gases. And what we can see here, if we look at the Amazon flowing into the ocean here, that there are almost no covariations in terms of variability between all these gases. So it gives us an idea of what processes are emitting it. This whole thing will be a little bit different in Asia, where we expect far higher methane abundances above background. So here we have about twice as high variations to be expected from the measurements. So with about more than 5% variability if you were flying over this spot here near Beijing. What we also see, methane, CO, and CO2 is highly correlated in these areas. So you can figure out that a lot of these combustion processes in these industrial areas are probably giving rise to these enhancements, and that could be a mixture of agriculture, combustion, and waste. And that's where the high spatial resolution also comes in. You need to really zoom in deeper and figure out where the point sources are, because at this scale, there's a mix of agriculture, industry, and waste. But to figure out how much comes from what, you can't just do an inversion or a satellite pixel of 10 kilometers because you have agriculture, waste, and the other processes within these 10 kilometers. So that's why we want to separate these point sources from the regional fluxes to basically get a better process-based understanding. Towards separating the point sources, what we specifically looked at is what is our point source capability with CarbonEye. This is a large eddy simulation of a point source of methane of 200 kilograms an hour. This is run at 5 meter resolution. You have kind of a 900 by 900 meter resolution element here. This looks like a disjointed plume. It actually came out of the same simulation. It's just the eddies kind of rips it apart at times, and you see these disjointed plume images in here. If you were to observe this with like a 1 kilometer by 1 kilometer pixel, this enhancement would be tiny because it's only like located in a tiny little area. I should mention our detection limits are very fine. So in principle, if you have a pure methane release somewhere, the thickness of a pure methane layer has to be just a little bit higher than a thin hair. I don't know, maybe this is a little thicker than my hair, 42 microns. So if you have a 42 micron layer of pure methane, we would be able to see it in the global mode. In the target mode, we co-add less pixels, so there we have about 150 microns. So now you can envision if you have a methane release somewhere from a pinpoint methane leak, if you have fine spatial resolution, you have a much higher likelihood to actually observe it. But what would we see if we see it in the target mode? We basically see a plume like this, where we tackle all of these resolution elements in here, and we would exceed it by kind of a Six Sigma level in terms of the enhancement divided by the noise that we expect to be in the scene. And even in the global mode, we will detect that it will just go down to like a 2.5 Sigma event. At lower wind speeds, it will, of course, go much higher than that because it would not be disturbed as turbulently as in this example here. This is just to show how we will tackle point sources as well, and we have machine learning techniques to actually derive fluxes directly from the plume imagery right now. But there's one other aspect that is very important for carbon eye, which is using a 2 micron range. This is an image of the Amazon. For people used to the US, they think like, oh, this is an agricultural field. This is maybe like 500 meters or whatnot. This is 10 kilometers. So this plume here with the biomass burning event, that whole plume is probably 20, 30 kilometers long. It looks tiny because the eye feels, and then this looks like, okay, this is maybe a tiny area in Iowa. This is in the red, green, and blue range, so kind of it's a false color image. How do you think this region here would look like in the near infrared at 2 microns? What would be different? Because our problem is scattering. If there's a smoke plume like this, we go like, photons do all kinds of stuff, so it's hard to quantify the real enhancement in the column. You can try to visualize it before I actually unveil it a little bit in your brain. At 2 micron, this area looks like this. The smoke plume is gone. You don't see anything anymore. It mostly has to do with the fact that these aerosols are relatively small, maybe less than 100 nanometers. And once you go to 2 micron, the wavelength that you're observing at is so much larger than the kind of physical dimension of the particle that it actually has a very, very low scattering efficiency. So you kind of see right through it. What you see is now the river. Clearly, you don't see a plume over this one, and this is really from the same day. I'm not faking this here. You see that it's from the same day because you're suddenly saturating your detector. This is from Sentinel-2. So the fire suddenly at 2 microns, you see really hot areas popping up because then the thermal emissions overwhelm the signal that you get back reflected from the solar radiation. So the 2 micron range can move in that domain. So we could detect the fire location. We can't see the plume anymore because it's not visible, but we see where it's happening, and we would be able to measure the enhancements in the other areas. An image that is a little bit closer to home, hopefully not too close to home. For some of us here, this is the fire that happened here in the area. I don't have a good picture for the Eaton fire because it was mostly cloudy for the times that we had actually good satellite overpasses. But this is the Palisades fire up here. So you see the Palisades fire, the smoke plume in the visible is flying over. You see it very nicely over the ocean because the background is less complex. In the near infrared, you don't see the plume at all. Even over the dark ocean, it's hard to see anything. And usually if you have smoke somewhere scattering over dark surfaces, they become very prominent if they are still there. But even over the darker ocean here, you can hardly see it. And this is what we think is really a big opportunity for carbon eye, just using the 2 micron band and not using other bands that are more towards the visible range, which might actually make retrievals worse in some of these cases, especially for fires. But I want to move from gases a little bit into other opportunities that carbon eye will provide, and this has to do with the land surface, because we are like the Swiss Army knife. We can do trace gases now with an imaging spectrometer like this, but we can also do minerals, which is better to remove surface interferences from the atmosphere itself, But we've taken spectra of different surfaces with the demonstration unit that I will show you later, and we can see that a lot of these spectral features in the land surface are actually a little bit higher frequency than we thought before. These are measurements with the demonstration unit for different lithium-bearing minerals, hectorite, magnesite, saprolite, and saponite, where we see that basically the values of these absorption features are only separated by 1 to 2 nanometers. If you have typical resolution elements with imaging spectrometers like EMIT that has a 7 nanometer sampling, you can't really differentiate these different minerals from each other as nicely as we would do if we had like a carbon eye instruments in there. And this does not only hold for minerals, which are of course of high economic interest, it also has to do with vegetation. This is an example of like fresh pine needles. They look almost a little bit boring spectroscopically. They have just a little bump at the 2.2 micron and then it decreases again. But once you have dried out vegetation, you actually see a lot more non-photosynthetic pigments and lignin structures at the higher wavelength site here. So this gives us information about fire fuel, like dried out vegetation that happened here basically in the beginning of the years could be quantified with instruments like this. On top of that, plastics are actually spectrally rich in this range. So we could find different polystyrene, HDPE bottles, and all of these things that have to do with plastics in the land surface that would also be detectable from space with an instrument such as carbon eye. But I want to keep a little bit of time for the demonstration unit. I will quickly go through that system here. This was actually quite amazing. We have a functioning imaging spectrometer that runs under vacuum and the temperatures as we have in flight. It was delivered on a very aggressive schedule, so they managed to get this built in only about 6 months. Some parts were things that were reused from the laboratory, but the core of the spectrometer is basically a new build. This was only possible through leveraging additive manufacturing, which is basically 3D printing of metals. So a lot of the structure was actually 3D printed. If you bring this to the shop and they should develop it, the lead time is about 6 months. So you would have to wait 6 months before you actually have your first metal piece in hand. And here we built the entire spectrometer within a 6-month time period. For the flight version, we will likely not use additive manufacturing because it's still a little bit too risky, but for the prototype, it was a great way of doing it. And we hope we can leverage it as well for the final unit. There's a paper from Christine Bradley in IEEE. She won the Best Paper Award for the optical design. But this is basically our carbon eye demonstration unit as built. And just to go into the main parts, so there's a detector which has the 3,000 spatial cross-track elements and 500 pixels for the spectral domain. This is the slit, which is one of the most important parts for the spectrometer. We have about a 36 micron slit width in here and a very long slit to illuminate the entire focal plane area. It's a Dyson spectrometer, so there's a Dyson lens in here and a very big grating at the bottom of the site, which actually disperses the light. But now you will see some of those parts in the video now that I want to show now. After I show the first light image here, this was kind of the first time we saw light in the warm system here with the spectrometer aligned here and there. Here we had like N2O and methane cells and all kinds of things that we could measure. So that was quite exciting. This is a little loud. I hope it's not too loud. This is a video that Adam Duran put together. He had the foresight to actually take enough images during the build and had like a time-lapse camera somewhere. And on top of that, the artistic skill to actually put together a video like this. And he was the lead engineer on the system, basically one of those. And he was so dedicated that he just put together that video. We didn't know of it. He was showing it to us, and I was like, okay, this gives me the chill, hopefully to you too. And he did the music and the editing. I don't know how he did this, but I'm a little jealous. So last but not least, it really takes a village, and I'm thankful to the entire JPL team to work on this. The hardware stuff is like, for me as a scientist who mostly works in front of the computer and gets data, it's kind of amazing to see how everything gets built up from scratch basically and building the instrument. Still a little unreal to me that there's a spacecraft flying in space actually looking down on Earth and I'm just analyzing the data. So thanks to the team at JPL, Takes a Village, and also Caltech and other places. Our next steps, we just submitted a concept study report. This is literally the concept study report, 2 binders full, about 800 pages. That was submitted a few weeks ago. A site visit where NASA folks, about 30 and 40, come down and grill us for 8 hours will happen towards the end of September. Hopefully, we will expect a decision by the end of the year, and we wish ourselves the best, but we still have a chance despite what's going around in the system here. And if you have any question, this is the larger science